In this module, what we're going to do is talk about the augmented design from a practical perspective. How do you construct an augmented design and how do you analyze it in R? So the experiment that I'm going to be talking to you about and that I'm going to be providing you data for is an evaluation of a nested recombinant inbred line population. This population that we're going to be working with today has some features of a NAM population. It's a series of crosses with parents in common. Okay, so there are really three main subpopulations, right? Each of them developed as a RIL. Okay, and the rationale for setting those subpopulations up was that each of the parents was selected as an elite line, so elite meaning it could be used as a parent in a commercial hybrid, but from a different subpopulation within our breeding program. And these subpopulations we tend to refer to as our O, our H, and our CA populations. CA because most of those have a pedigree and genetics that trace back to material that would be used in California. And the O and the H are natural subpopulations within the Ohio breeding program, probably tracing back to origins with Midwest and East Coast breeding. Okay, so the population consisted of 288 individual lines, and we evaluated it in 2 years over 2 locations. These 2 years happened to be the wettest in history in Ohio and the driest in history in Ohio. So we feel like we captured a lot of environmental variation with this 4-location study. Okay, and in order to make this feasible, each environment, in other words, each farm in each year, was grown as an augmented design. So let's see what this looks like in the real world. So here's a field planting out in Fremont a couple of weeks after transplant. So the plants have begun to grow. We can go ahead and superimpose our tier. So we're looking down a tier right now. Okay, and then we have this column of 3 beds, right? And then a quadrant is going to represent a group of rows and columns. So here's a map of what the trial looks like. Okay, and so every square on this table represents a plot. So a 20-foot long row of 20 plants. Okay, and so we have tiers 1 through 36. We consider a group of 3 plots to be a row. So we have this column is a tier, then we have a row this way. Within there we have quadrants. Okay, so 9 sets of 3 separate columns, that's a quadrant. So what I want you to notice is that within every row and every column and every quadrant there are at least 3 checks. Okay? And it's these checks that are used to normalize our data. In our design, we can account for variation along this dimension, or within quadrants. And if you think about what might happen in a field, our fields are rarely planed like they might be out in California. So we get a little bit of slope here, we get low spots. There might be an edge of the field where the water collects. And so if water were to collect along this edge, we should see that as a row effect. If it was to collect at the beginning of the field, we should see it as a column effect. If it sits in a corner, or if there's a low spot, we should see it as a quadrant effect. Okay, so if we use this augmented design, consider our checks and treatments to be random, and extract a best linear unbiased predictor, we're going to have a model adjusted mean where the mean is adjusted for the terms in the model. And so if we put tiers, rows, and quadrants into our model, we're going to correct for the variation. Okay? Now, having said that, this layout also allows us to take other approaches. We could normalize everything to the nearest check, as an example.